Right, for all the grade 12s that are watching this recording, this tutorial, we are starting the new unit, I wouldn't say topic, but new unit of momentum, which is called the conservation of momentum. Okay, and with everything, we always need to define what is conservation of momentum, or what is known as the law of conservation of momentum. And that law states that the total linear momentum in an isolated system, which we'll explain the term of that a little bit later. An isolated system is constant, but constant in magnitude or size and direction. Can't even spell and right, shocker. And direction. Right? That is the law of conservation of momentum. Okay? When they ask you to state the law, conservation of momentum, that's what they mean. Total linear, by the way, linear has an R at the end of it. My bad, my spelling might be off today. An isolated system is constant or remains constant in magnitude and direction. So a couple of important terms that we're just going to have to discuss quickly. And one of those important terms being what is an isolated, or rather, what is a system? A system is obviously a small part of space, all right, that we consider, all right, for investigation of a particular problem that we want to solve. Anything that is outside of this little system is called the environment, all right? So it's almost, think about it as actors on a film set or a film set crew. They film in a specific part of a city, or they film in a specific part of a town, or wherever they're filming. And the camera only catches what we see on screen. Everything outside of the film crew's setup would be normal life, normal environment. All right? So that's whenever you see a film crew on a film set, they only film within that desired space or system. All right? Same thing. That's what a system is. Okay? Now, let's discuss what's an isolated system. All right? An isolated system, let me just underline it here. An isolated system, that is where, or a system on which that F net equals 0. All right? F net equals 0 newtons. In other words, its value is 0, which means it excludes all external forces that originate outside of two objects that are colliding. All right? Because that's what usually we test momentum for, or conservation of momentum for. For example, an isolated system, there'd be no friction. All right? Only internal forces would be considered. Now, we've just mentioned another two terms: internal and external forces. All right? So, let's go with that one. Let's explain or define internal forces. Okay? Internal forces, all right, are, of course, forces that objects exert on each other. Okay, they exert on each other. All right, within a system. All right, so everything happens within this little system. All right, and examples of that would be your contact forces between them when they make contact. So contact forces. And gravitational force. Those will all be external forces. Oh, sorry, internal forces. I don't know what I'm talking about. Sorry, internal forces. All right. So if we have an isolated system, we are trying to calculate, measure the conservation of momentum between two cars colliding with each other. Of course, that contact force would be an internal force as well as gravitational force. Okay. Now, I don't think I'm going to have enough space on this little slide to write down the definition for external forces. All right, which I will obviously revert to the next slide for it. Although I will try and give it a shot. All right, external, of course, which is outside forces. All right, forces, which I mentioned already now, from outsiders, the system or a system. Okay, and they act on objects. So I'm going to divert over here on objects that are also within the system. I'll use another color for example. Let's pick another color here. Let's see this one. Example. Okay. We have force applied. So applied force. Alright. Frictional force. So if I write it like this. Okay, now let me just write the whole word out. Frictional force. I'll just say frictional. Air resistance. Alright. So I'll just put air. Tension, of course, which we're very well familiar with. Tension. And which would be tension in a rope. And force on a car or force on a rocket. Those would all be external forces, but mainly applied force, frictional force, tension in a rope, or air resistance would all be external forces. Usually in questions we'd say ignore the effects of air resistance. In that case we'd only look at force applied and frictional force as being external forces. So the formula for in symbols for the law of conservation of momentum. Let's write it out without symbols first, or let's mix it up in words and symbols. So total momentum, P initial, is equal to total momentum, or P final. Okay, put that in symbols. We make use of sigma. All right, sigma, which is sum all. All right, sum all, or which is total. Sigma pi equals sigma pf. Total momentum before equals total momentum after. Total initial momentum equals total final momentum. I've literally saying the same thing over and over, just in a different, slightly different way. Okay? Meaning that one, when objects collide, all right, and then they'd obviously move away from each other, but think about it, when they collide, all right, they're going to make some type of collision. So let's take the example of snooker balls. Right? Everybody's played snooker or pool before. Okay? If you never played it, you know about it. Okay? So we have our formula for the snooker ball. So total PI equals total PF, which means I'm obviously going to have two different snooker balls here. So this would be object 1 or ball 1. And number 2 would be object 2 or ball 2, meaning that therefore if I expand this formula I will have PI1 plus PI2, because if two snooker balls are colliding with each other they must have momentum of their own individually, right? But when they collide, two snooker balls, they obviously move away from each other. All right? They move away from each other. All right? So then they must have a final momentum too. PF1, the final momentum of the first snooker ball, plus the final momentum of the second snooker ball. Okay? We can further expand this because remember, this is the law of the conservation of momentum, but take you back to week 1. P is equal to mv. And I see a lot of P's there. Therefore, finally, m1 vi1 plus m2 vi2 is equal to m1 vf1 plus m2 vf2. How do we read that? The mass of the one snooker ball or the one object times the velocity of that one object plus the mass of the second object times its velocity, i.e. the velocity of the second object, is all equal to the mass of the first object times its final velocity plus the mass of the second object times its final velocity. If that is all equal, then it is correctly assumed that total linear momentum is therefore conserved. And that's the formula. Alright, the only time this formula will change is if the objects collide and they stick to each other. In which case, the right-hand side, i.e. this side, will change. Alright? Which I'll show or demonstrate in just a second. Okay? This was the first type of example. Okay? If you have a second type of example, let's have cars collided. Alright? And stayed attached. Okay, now don't worry, I'm not going to work here. I'm going to, I spelled attached incorrectly. Please forgive me. Okay, I'm not going to work in that little small space. Okay, I'm going to move over to the other slide. Now everything over here, this part on the left hand side stays the same. So I'm just going to skip to this bottom part over here for example 2. So again, just putting 2 over here. So I have m1 vi1 plus m2 vi2. But now remember, objects are now attached to each other. So we have the predicament where m1 is technically a part of m2 now. They have collided and they've stayed attached. Therefore, we take mass, or we take Vf as the common factor out. I'll end up with that. This is if the objects have collided and they have stayed attached and they have not broken away from each other. But there are 2 types of collisions that will occur within momentum. Okay, now this is quite a lengthy definition. I'm going to choose a brighter color for it. Is that a collision is considered elastic. Okay, and I used to like these types of questions back in the when I was a scholar. If the total kinetic energy Ek, okay, which we're all very well familiar with, kinetic energy, Ek, okay, of the objects, that's a T, of the objects, in the system, during the collision is conserved. Now, when I mean is conserved, similarly to the law of conservation of momentum, is that i.e., and we'll come down here, ek initial, or the total ek initial, must be equal to the total ek final. Total kinetic energy before must equal total kinetic energy after. Okay? If this is not the case, which would be otherwise, if that is not equal, collision is inelastic. So the collisions are only said to be elastic if the kinetic energy, or the total kinetic energy before the collision of the objects, is the same as after the object has collided. Have collided. Otherwise, if it's different, if before differs from after and vice versa, the collision is said to be inelastic. Okay? Obviously, we know kinetic energy is the energy that an object has because or due to that object's motion. Okay? So if we have the formula for an elastic collision, right? Elastic collision, it'll be a formula where we have, of course, this formula, which I'll expand, which will be half m1 vi1 squared plus half m2 vi2 squared must equal to half m1 vf squared plus half m2 vf2 squared. Okay, I know I didn't have a 1 here. Let me put a 1 there quickly. Okay, so just to read that again, half of the mass of the first object times the velocity of the first object squared plus half the mass of the second object times the velocity of that second object squared initially is all equal to half the mass of the first object times that object's final velocity all squared, or velocity all squared, plus half the mass of the second object times the velocity of the second object's final velocity of the second object, all squared. Okay, the velocity part is only squared, by the way, not the mass. Okay, as you all should know. And if those two are equal, then we have an elastic collision. And of course, if it is not equal, then to come over here, inelastic, how the formula would look is just that total, just put a line down here and a line underneath here. EKI will not equal total EKF. And that's the simplicity of it. But collisions in real life are almost never elastic. Collisions are almost. Okay, so an inelastic collision, which is a bit more practical, would be the example of two cars colliding during and join during a collision. All right, so an accident between two cars, but the cars stay joint. Okay, that's an inelastic collision. A elastic collision, which almost never occurs, the snooker balls. All right. The collisions between snooker balls are almost elastic, and balls that bounce very high also have a almost elastic collision with the ground. So like those bouncy balls would be, I mean, they have a super normal bouncing ability within them because of the properties of the ball itself that allow it to bounce that high. For example, higher than a tennis ball, higher than a basketball, higher than any other type of ball that can bounce. So those two would be examples of almost elastic collisions. And that concludes the topic of the law of conservation of momentum and elastic and inelastic collisions explained. And that also concludes this chapter on momentum and impulse. Alright, we'll be starting a new topic in the next video series, which will be vertical projectile motion. So you don't want to miss that. Stay tuned for more video tutorials.